Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I will explain CFD analysis and optimization of a condenser heat exchanger. This one will be done using SolidWorks flow simulation. The model is already made using SolidWorks. It is assembled. It is made up of copper tubes and the fins are made up of aluminum, right? So to start this analysis from flow simulation, then we have to create that environment of flow simulation using wizard. Let's take the name of the project as project 1. We will consider the unit as SI unit and temperature will take as degree centigrade. Next, it is an external analysis and by the same time we have to take heat conduction in solids. Here in this case convection will also occur, therefore we are considering gravity. Next, and gases, two gases will be there. One will be the default gas will be air, and inside the copper tubes we will consider freon gases. As real gases, we will take freon R123. Next, as I told already, the fins will be made up of aluminium and the copper tubes, that material will be provided later on. Next, the default velocity of roughness we are taking. Let us consider velocity of air will be 20 meter per second. And very important thing you can see that in this case air will be passing in the Z direction. So this reference axis we have to select, coordinate axis should be Z. Okay, and temperature of air is 30 degrees centigrade. By the same time, velocity of air equal to 20 meter per second. Let's finish it. Now you can see the computational domain is created. It is the volume through which all the calculations will be taken care of. It is better to reduce the volume of computational domain. Edit definition. We will reduce the volume. Now our computational domain is ready. Green check, and let's hide this domain. Next one, we have to apply some boundary conditions. First of all, we will apply the fluid subdomains because we are considering two fluids. Freon will be passing through these copper tubes. Insert fluid subdomain. Now we have to select what fluid will be there. We are considering freon only through these copper tubes, and freon will be having temperature minus 5 degrees centigrade, and that will be passing through these tubes. You can see this is the fluid subdomain for freon gases. Okay, green check. Next one, we have to apply our boundary conditions and solid materials also. Solid materials, we have already provided aluminum and copper to be provided right now. Insert solid materials, predefined metals. It will be aluminum to be provided for all these fins. So we have to select all these fins. Aluminum is provided for the fins. Now we have to provide copper tubes. Insert solid material, predefined metals. It will be copper for the tubes. So we have to select the tubes. What we will do is, see tube selected, copper is provided. Done. Next one, we have to apply boundary conditions. Insert boundary conditions. freons will be passing through these copper tubes at a rate of 0.01 kg per second, and its temperature will be definitely -5 degrees centigrade. And substance concentration, it will be only freons, so 0 air, and refrigerant freon will be 100%, that is concentration 1. So to select that inlet, select other, face, green check. It is done. Now another boundary condition to be applied. Insert boundary condition, that should be atmospheric pressure at the exit pipe. Select other, green check. Now the last boundary condition to be applied, that is the walls of this condenser should be having convective heat transfer coefficient of 90 watt per meter square degree Kelvin. Boundary conditions, insert boundary condition, walls, it will be real walls, and it will be convective heat transfer coefficient of 90 watt per meter square degree Kelvin, and temperature will be 30 degrees centigrade. Let's select that fins. You can select from the original body. All the fins have been selected. Green check. All the boundary conditions have been applied properly. Now finally we have to select the goals. Lot of goals can be selected, but two types of goals you want. Insert global goal. We will take maximum temperature of fluid and maximum temperature of solid. By the same time, what is maximum wall temperature? Green check. And one surface goal also we want to consider. Insert surface goals. And take maximum temperature of fluid and maximum temperature of solid, at the first plate we are selecting, green check. So all the goals have been defined properly. Now we can run this. Let's run it. It has already started running. We can see the solver window. It will take long time for these calculations and iterations. Whenever it finishes, we'll see the results. Let the iterations move on. The solver window has finished its calculations and iterations. We can check the results from the solver window now. This is the graph of all the results together. We can see separately also. Like first one is showing the global goal of maximum temperature of fluid, that is maximum temperature of freon gases. It started with 30 degrees centigrade and finally it has come down to a fixed value of 30.841 degrees centigrade. And maximum temperature of solid, that means the temperature of that copper tubes, it is 28.1605 degrees centigrade. And maximum wall temperature, that is wall temperature of the fins or wall temperature of these aluminum fins, has come down to 28.1605 degrees centigrade. Initially its temperature was 30 degrees centigrade, and because of cooling the wall temperature has reduced. It has come down to 28.1605 degrees centigrade. Next one, we want to see the surface goal, maximum temperature of fluid at the inlet and exit end of this freon gas. As you can see, it is the location where the front plate was located. Its maximum temperature of freon gas at this location is 26.2815 degrees centigrade. All this information you got from our solver window, right? Let's close it. If you want, we can view the results from the actual cut plots also. Now we'll see the results from the cut plots. We have to load the results, and first of all we'll see cut plots. Insert cut plots. Across the front plane we'll see temperature of fluid. Green check. For visualization, it is better to make the object transparent, then it will be easier to view that temperature graph. We'll make this one transparent completely. Okay, so cut plot 1, we'll make it clear and hide. For making transparent for this object, we have to go back to the model again. We'll select all these fins. This is transparent right now. Again, these few numbers also should be transparent. And the pipes also have to make it transparent, right? Change transparency. This transparency, now we have to make the pipe also transparent. We can select the pipe. Pipe is also transparent. Now we can view the flow of fluids and temperatures distribution in a better way, right? Want to see the cut plots? Let's see the animation. You can see from the top, that is from the inlet, temperature is coming from minus 5.36 degrees centigrade, and at the exit temperature is high little bit. It is in the range of 20 to 23 degrees centigrade at the exit point. So you can see very clearly that here it is blue line, but I will analyze this one from the cut plot drawing itself. Clear and hide. Cut plot 1, edit definition. Want to see from a specific plane. Want to see this one from, maybe we'll check from side, and want to see cut plots from the middle of this plane. Okay, let's see. Yes, it is visible. The color change is providing the actual temperature distribution of this freon gas throughout this passage. So this is the entry. From entry point you can see the color is actually blue, and finally while at the exit point it is in the range of yellow color. So that means at the entry point temperature was in the range of minus 5.36 degrees centigrade, and while passing through these pipes its temperature was ranging from minus 5 to 23 degrees centigrade, and at the exit the final temperature is 23.64 degrees centigrade. Okay, we'll see the cut plot in the form of animation. It's clearly visible. The temperature at the inlet is less, equal to minus 5 degrees centigrade, and while passing through this tube at the exit its color is changing. It is in the range of 21 to 23 degrees centigrade. Okay, we can have this one from other plane also. We'll clear and hide this part, and want to see this from right plane. Cut plot 1, edit definition, we want to see from right plane. We'll change the plane, right plane, want to see. Again, it is also showing the same behavior. That is, top we are having the inlet, cold freon gas is moving from top to down, so inlet temperature is less, minus 5.36 degrees centigrade, and while at the exit end its temperature is in the range of 20 to 23 degrees centigrade. Okay, we'll show this one in the form of animation also. Play. Okay, let's clear and hide this part. Next one will show something, surface plots. Insert surface plots. Want to see from all surface, use all surfaces. Want to see temperature fluid along all surface of this condenser heat exchanger. It is very nicely visible. So across the fins you can see the temperature is in the range of 23 to 27 degrees centigrade across the fins, and the freon gas while passing through its covered tubes, its temperature is in the range of yellow, that means in the range of 20 to 23 degrees centigrade, and at the exit end its temperature is in the range of 23 to 27 degrees centigrade. Okay, you see backside also almost similar type. Backside is having temperature range of 23 to 27 degrees centigrade. Little bit of red zone we can see at the lower back corner. Here it is in the temperature in the range of 27 to 30 degrees centigrade. Okay, next one we'll do very important thing. We'll see flow trajectories. This part clear and hide. Now we want to see flow trajectories. Insert flow trajectories. It will show the passage of freon particles from inlet to outlet, and the numbers, instead of 20 we can make it 50, and we want to see in the form of arrows only. Our target value to see temperature of fluid, right? So it is locate the passage, select other, green check. Particle study is ready. Very nice picture. You can see that at the entry its temperature is in the range of 30 degrees centigrade. You can see the freon particles moving from inlet to exit end. At the entry point its temperature is in the range of minus 5.36 degrees centigrade, and while passing through these tubes at the exit end its temperature is in the range of 23.64 degrees centigrade. You can see the velocity also. Let's see the velocity of fluid particles. Velocity remains almost constant, it is not changing that much. It is in the range of 13 to 26 meter per second. We got temperature fluid. Now we will to see total temperature. It is also the same representation of what we saw in case of fluid, right? Now do one thing, we will see this one in the form of animation. Flow trajectories, clear and hide, and what you see in the form of animation. Play. You can see from all sides. Let's see this one in isometric view. Let's clear and hide this part. Next one, what you see the results, right? So that results will come from goal plots, insert goal plots, and want to see all the goals. The goals we have already seen from the solver window itself. These values we can see in the form of graph also, from summary and history. We've already seen these results from the solver window. That first one is actually temperature of fluid. It has conducted near about 300 numbers of iterations, and with that iteration you can see the results. That initial temperature of fluid was that was maximum temperature of fluid. First one is maximum temperature of fluid, started from 30 degrees centigrade. It has gone maximum up to 33.35, and finally it has come down to 30.85 degrees centigrade. Second one is also wall temperature of these fins, started with 30 degrees centigrade, and after 300 numbers of iterations it is stopping at 27.85 degrees centigrade. Maximum temperature of wall. Okay, again next one is the maximum temperature of solid, that is the temperature of these copper tubes. It started with 30 degrees centigrade and it has come down to 27.85 degrees centigrade. Next one we can see surface goal, and that means the temperature of fluid at the front plate. It started with 30 degrees centigrade and finally it has come down to near about 26 degrees centigrade approximately. Okay, and the last one, it is the surface goal maximum temperature of solid, that is the front plate temperature. It has started from 30 degrees centigrade and finally it has come down to near about 25 degrees centigrade. Okay, we can see all these results in the form of data or in the form of graphs. These are in the form of summary, the results you can see, right? Okay, so from here we have to optimize our analysis. You can see the maximum temperature of fluid is 30.89 degrees centigrade, right? So what is our aim? Our aim should be to reduce this maximum temperature from 30.89 degrees centigrade to a specific one. Say we want to reduce the maximum temperature from 30.89 degrees centigrade to 25 degrees centigrade. For changing this one, we have to do a lot of iterations and we have to provide some kind of input variables. Let's, in this case, input variable will be mass transfer rate. Initially we have transferred freon gas at the rate of 0.01 kg per second. Let's start our optimization. It will start from new parametric study and goal optimization. And as I told earlier, for optimization you have to depend on some input variables. Let's take these variables from boundary conditions. Boundary conditions, inlet mass flow rate. We are taking inlet mass flow rate as a input variable. Okay, let's take that range for input variables 0.001 to 0.005. Let's take it, and we have to see the criteria. Criteria is dependent on goals. We have a lot of goals. We are planning to fix the temperature of the wall to be 25 degrees centigrade. So selecting wall temperature, green check, and target value should be 25 degrees centigrade. And we want a deviation in the range of plus minus 0.1 degrees centigrade. Done. Now see the scenario and let's run it. Iterations have already been started. First it will start with the maximum mass flow rate. It will find out the fluid temperature and then it will take the minimum value. In this way it will try to narrow the gap, and finally it will optimize our freon temperature. Okay, let's the iterations move on. Whenever it is finished, we'll see the results and analyze it. First iteration is already over, and from the solver window you can see the results. We had 5 set of goals. In the first iteration you can see that maximum temperature of fluid equal to 30.86 degrees centigrade, and maximum temperature of solid, that means the temperature of these copper tubes, equal to 25.45 degrees centigrade. Maximum wall temperature is 25.45 degrees centigrade, which is very close to our desired output. Our desired goal was to have a wall temperature of 25 degrees centigrade. And you can see the maximum temperature of fluid at the surface equal to 19.63 degrees centigrade, and maximum temperature of solid at the surface equal to 19.63 degrees centigrade. These two temperatures are at the inlet and outlet side of the condenser. Okay, and we got the wall temperature to be 25 degrees centigrade at a mass flow rate of 0.001 kg per second. Okay, so we got our desired goal by this optimization. Thank you so much for watching this video. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.